my name is Deyan Mihaylov, and today we are recording at the Albert Einstein Institute for Gravitational Physics. Now, in order to help you understand what black holes are and why they're so interesting, we need to go through several topics. First, I'm going to explain to you what this term means and what black holes are. Then we're going to speak about some of their properties. And finally, we're going to discuss the observations of black holes and what is the evidence for them in the universe. Now, before we talk about black holes, there are several fundamental concepts that we should revise. And let's start with our understanding of the theory of gravity. The story begins more or less with Sir Isaac Newton and his theory of gravity from the 17th century. What Newton said is that the force of gravitational attraction between two bodies is proportional to the masses of these bodies and inversely proportional to the distance between these two bodies. And this was absolutely revolutionary because no one so far understood how exactly gravity behaves. So this was a fundamental improvement in our understanding of gravity. Now, it turned out later that Newton was only partially right, and Einstein provided a more complete picture of our understanding of gravity. What Einstein said in his theory of general relativity is that what Newton said, is only a partial understanding. And in fact, the full story is that geometry of space-time in our universe can be related to the distribution of mass and energy in the universe. The last thing that I would like to mention at this point is the concept of escape velocity. This concerns the fact that you need to be moving at a fast enough speed in order to escape the gravitational acceleration of a body. All of us have seen rockets taking off from Earth and reaching space. And even though we see how the rockets take off vertically, the vertical speed and acceleration is not what matters. It's the horizontal speed and acceleration that is what matters in order to get that rocket to reach space and stay there. They have to reach a certain very high velocity around the Earth in order to be able to escape the gravitational attraction. The next thing that we should mention is about the speed of light. Now, even though the speed of light is very high, it is only finite. And not only that, but it has been discovered that nothing in the universe can move faster than the speed of light. To help you imagine how fast the speed of light is, it only takes 8 minutes and 20 seconds for light to reach us from the sun to the Earth. It only takes 2.5 seconds for light to reach from the Earth to the moon and back. And inside 1 second, light can make 7.5 trips around the world. So if you send an object which moves at the speed of light around the Earth, in an orbit around the Earth, in 1 second, it will circle it 7.5 times. That's how fast light is. Let's talk about black holes. Black holes are, in their essence, objects which have become so heavy and dense that their escape velocity, that we just talked about, has become larger than the speed of light. What this means in practice is that nothing, not even light, can escape these objects. And that's why when we look at them, we basically see a black body, because there's no light originating from it that we can see. That's what we call a black hole. Now, black holes don't have a definite surface like planets or stars do. What we see when we look at a black hole is the so-called event horizon of the black hole, which is an imaginary surface that once you cross it, you will fall into the black hole. There is no way to escape the gravitational pull of the black hole if you get closer to it than the event horizon. Let's talk about how big and heavy black holes can be. The masses of black holes start from around several solar masses and go up to tens of billions of solar masses. So there is a very big range of masses for black holes. But what is important is that even a black hole that is several solar masses can be condensed in a size that is several tens of miles across. Because there is such a variety of masses and sizes, scientists have started to classify black holes according to their size. Small black holes that are no more than, say, 10 solar masses are called low-mass black holes, and they are usually very compact, so they can be very small objects. The really big ones that are several tens of billions of solar masses are called supermassive black holes. And we also have anything in between that we call intermediate mass black hole. Let's talk a little bit about the masses and sizes of black holes. Now, when we talk about how massive a black hole is, we usually measure it in units of solar masses. So we say how many solar masses is the mass of a given black hole. Now, the mass of the sun is about 2 times 10 to the 30 kilograms. So that's 2 and then 30 zeros after that. Kilograms is the mass of the sun. And the lightest black holes start at several solar masses. The heaviest black holes go up to tens of billions of solar masses, and those are really, really massive black holes. In terms of sizes, the smallest black holes could be very compact objects, even though they pack several times the mass of the sun. They could be no bigger than maybe several tens of kilometers across. The largest, most massive black holes can grow up to be much larger than the size of the solar system. So we have a big range both in the masses of black holes and their physical sizes. The reason why scientists have classified them in these categories is because they differ in the way that they form as black holes. Low mass black holes usually form as the product of stars. The reason that a star shines so brightly is because there are very intense thermonuclear processes inside the star which produce all this light. But at a certain point, a star runs out of fuel and several things can happen. It could explode as a supernova. It could become a giant and slowly die away, or if it is massive enough, if it can collapse onto itself after it expends its fuel. So what happens is that literally the star, after using up all the fuel, collapses onto itself and condenses into a very small region of space. And that is how a black hole forms. Who came up with the idea of black holes? Even back in the 1800s, people theorized about possible objects which are so heavy that their escape velocity is larger than the speed of light. Einstein later on confirmed that they can exist within his theory of general relativity. But even after that, it took several more decades until we got the first observational evidence of black holes. The way in which we detect the presence of black holes is also very interesting because, as you can imagine, it is very challenging to detect an object which doesn't emit any light. Now, the way that we establish the presence of a black hole somewhere in space is by observing the stuff and the matter that orbits this black hole. For example, the black hole at the center of the Milky Way, Sagittarius A star, this is what we call a quiescent black hole. It means that as opposed to an active black hole, it has stopped accreting matter from the surrounding bulge of the Milky Way. This black hole is what we call a quiescent one, as opposed to an active supermassive black hole, which still accretes matter from the galactic bulge surrounding it. Sagittarius A star doesn't do that anymore, so we cannot even see a disk of gas surrounding it. But what we can observe are the orbits of stars just around the black hole. And from the orbits of these stars, we can calculate the mass of the object that they are orbiting, and we can measure the radius of that orbit. And if we calculate how much mass is contained within that diameter of space, we can establish that the only possible explanation for that object is that it is a black hole. I can erase it again. Another way to know that there is a black hole somewhere in space is by observing its effect on other celestial objects that are directly behind it. For example, if we are looking in a certain region of space and we notice two copies of the same star at two different positions, what we can realize is that this is not the same, these are not two separate stars, but it is the same star, and the light coming from that star has been disturbed by a black hole, which has produced two copies of the image on two different points of the sky. Even more interestingly, we have now discovered black holes merging, collapsing together and becoming one black hole. And since 2015, we have the means and the technology to detect these mergers of black holes and listen to the gravitational waves produced by them. Even more interestingly, we have also detected the collision and merger of two black holes to produce one. And in this process, we have also detected the gravitational waves that were produced by this merger. The gravitational waves are actually a direct consequence of Einstein's theory of gravity, according to this equation. If two black holes were spinning around each other and about to merge, this directly translates to ripples in space-time, much like the ripples in a pond if you throw a rock in it. And since 2015, we have the technology and the means to detect and analyze these gravitational waves. These gravitational waves have actually provided us with a wealth of information about the black holes, because each time that we detect a gravitational wave, we actually can study three black holes. The two black holes that merged together and the black hole that was produced by the collision. And by analyzing the data from these gravitational waves, we can learn about the masses of the two black holes and the third one that was produced. We can measure the spins of the black holes, that is, how fast each black hole was rotating around its own axis, much like the Earth rotates around its own axis. We could also measure how long it took for these black holes to merge, and we can understand how far away from us this happened. As an instance, the first pair of black holes that we detected merging, this actually happened 1.5 billion light years away from us. What this means is that the signal from this collision, which by the way travels at the speed of light, took 1.5 billion years to get to us. So it happened 1.5 billion years ago. And this was around the time when the first cellular, multicellular organisms were forming on Earth. Even though over the past century we have learned a great deal about black holes, there are still a number of open and unresolved questions about them. The most interesting and pressing of them is what happens inside a black hole? What is there inside a black hole past the event horizon? Now, we know that at the center of a black hole sits the so-called singularity, which is where you eventually end up if you fall into a black hole. However, what is the internal structure of a black hole is still a very open and interesting question. An interesting aside here is what happens if one falls into a black hole. Now, because of the very strong gravitational forces that act upon you as you fall into the black hole, what happens is that you would gradually be stretched in one direction while at the same time squished in another direction. So you would gradually become very thin and very long, much like a piece of spaghetti. That's why this process is actually called spaghettification. Now, this would eventually result in your unfortunate death as your limbs and other body parts are ripped off from you. But unfortunately, this is what happens when one falls into a black hole. Another open question concerns the areas of the event horizons of two black holes as they merge. Stephen Hawking, the famous British astrophysicist, proposed a theory about the event horizons of black holes as they merge. But this theory also left a number of unanswered questions that we are still trying to resolve. Another issue, a very interesting open question, is what happens to information as it falls into a black hole. Since a black hole is uniquely described by three parameters, its mass, its spin, that is how fast it rotates around its own axis, and its electrical charge. This means that any information about any body that falls into the black hole is inevitably and irretrievably lost. Now, this goes against some of our established notions about physics and information theory. And therefore, this is a problem that me and some of my colleagues here at the Max Planck Institute are trying to resolve. I first became interested in physics and astronomy when I was very young, maybe 4 or 5. And I started asking questions like, how big is the universe, and how come the universe is infinite? And I realized that the answers of these questions that I received back then did not fully satisfy me. And I decided that it would be really cool if one day I can contribute to our better understanding of the universe and what happens in the sky very far away from us. In order to become a physicist, the most important quality is to be curious. If you're curious about the world around you and you want to get a better understanding of it, everything else will come naturally. You would have to learn a lot of new concepts, you would have to study mathematics and physics, but eventually you have all the tools that you need in order to work and excel as a scientist.